Hi all, I am Jihaz Khan. I am working as a specialist on electric vehicles and autonomous driving validation in Tata Elxsi. Today I would like to take a webinar on eMobility HILS, Scalable Validation Framework for Electric Vehicle Components. This is the agenda of today's discussion. We will start with an overview of Tata Elxsi. Then we will have an introduction about electric vehicles or EV. We will then discuss about the challenges in the validation of EV electronic control units or ECUs and move to the core of the webinar, which is using eMobility HILS for addressing these challenges and in the validation of DC-DC converters, battery management systems or BMS, motor control unit, inverter and onboard charger module or OBCM. We will also discuss about the validation of various EV standards. Then we will summarize the advantages of eMobility HILS. We will consider one case study of DC-DC converter validation to explain the business model and savings achieved when using eMobility HILS. This slide gives an overview about Tata Elxsi. Tata Elxsi is a technology-led design services company headquartered in Bangalore, India. We connect the finer aspects of design, content, and technology to create great experiences for the consumers and exceptional outcomes for brands and businesses. We do consumer research, technology consulting, product design, development, testing for various industry sectors like transportation, broadcast, communications, healthcare, etc. This is enabled through a core team of 6,500 plus engineers and technologists who work from different locations in India and service our global clients. In automotive, we work for the last 20 years and brings together a world-class artificial intelligence and analytics practice, an award-winning HMI and design team, and ASPICE Level 5 certified automotive engineering to drive solutions for the autonomous and connected cars of the future. This slide speaks about the EV market trends. Studies suggest that by 2040, 35% of all light-duty vehicles on road will be EV. Therefore, we need to improve the cost and efficiency of EV components in coming years. Design, development, and validation of EV components will witness a huge market interest. OEMs and Tier 1s are in a race to keep up with these challenges. So the question is, how ready are we? A basic know-how of EV vehicle components, its functions and architecture is essential to understand this webinar. This figure shows a high-level architecture of a battery electric vehicle or pure electric vehicle where components highlighted in blue are under the scope of validation considered in this webinar. A high-voltage battery pack serves as the core energy source of EV. Batteries are mostly made of a number of lithium-ion or lithium-ion phosphate cells in series and parallel. These cells are monitored and maintained by an ECU called Battery Management System or BMS, who is responsible for safe operating conditions and long life of the battery through proper charging, discharging, and cell balancing. Motor Control Unit or MCU, along with the inverter, converts the battery DC voltage to AC for exciting the traction motor which is connected to the wheels, where energy transfer happens in this direction. Similarly, for regenerative braking, motor acts as a generator and the AC voltage generated is converted to DC and stored in battery, where energy flows in this direction. Motor control unit and inverter are responsible for achieving the required speed and torque at the wheels. Electric vehicle supply equipment or EVSE provides proper AC to OBCM. OBCM converts AC to required DC voltage with proper charging current required. OBCM is responsible for communication with EVSE, with BMS to assure safe and efficient charging. Modern OBCMs are also capable of supplying energy from battery pack to grid also called vehicle to the grid. DC-DC converter or DC-DC as shown here provides the power translation from HV battery pack LV loads in the vehicle and the LV battery. Bidirectional energy transfer is also a feature of DC-DC converter where the energy can flow from LV network to HV network as well. Keeping the EV architecture in mind, let us see how we can validate each of these components in a lab-based environment. Hardware in-the-loop simulation or HILS is a widely used solution for ECU validation. Real ECU is made the device under test where the plant or combination of sensors and actuators is simulated using intelligent software which we call plant model and real-time hardware which we call HILS simulator. National Instruments, DSpace, Vector, etc. are some leading manufacturers of HILS simulators. Plan models are created using programmable environments like LabVIEW, Simulink, etc. Let us take DC-DC converter as an example here. Concepts we are going to explain can be extended to any ECU in general. Assume that you have removed DC-DC converter from vehicle and kept it inside a lab. In real vehicle, DC-DC converter has HV battery pack and loads like traction or BIS-G motor on one side and LV battery and loads like HVAC systems or LV loads on the other side. When we create the HILS system for DC-DC converter, DC-DC converter becomes the device under test. HV battery is replaced by a programmable power supply and HV loads are replaced by a programmable load or DC electronic load, while LV battery is replaced by a programmable power supply and LV loads are replaced by a programmable load. All programmable devices are connected to a real-time HILS simulator hardware. HILS simulator houses the plan models which mimic the behavior of real-world battery and loads. HILS simulator asks the supply and load to implement this behavior. At the end of the day, DC-DC converter thinks it is actually connected to the batteries and loads as in real vehicles and we can perform validation of DC-DC converter. Main advantages when using HILS are wider test coverage. In our example, using a programmable power supply and load allows you to vary voltage and current to take any values, which cannot be achieved in real vehicle. Fault insertion allows you to create faults in ECU pins and see how well diagnostics work. Reproducibility, you can re-execute the same test case again and again. Early time to market, no need to wait for proto cars or real plan to be ready. Cost efficient when compared to proto cars and real car testing. Let us take a look at the challenges in EV ECU validation. We can start with scalability of HILS, where we need to validate ECUs with various operating ranges, and this is in line with the title of the presentation. Let us take DC-DC converter as an example for our discussion. The discussion which we are going to have can be extended to any EV ECU in general. Automotive DC-DC converters can have a rating anywhere between 1.3 kilowatt to approximately 10 kilowatt. And if you take a look at the input and output rating, voltage and current for a mild hybrid vehicle, for a car BEV or even a truck BEV, you can see how diverse the ratings are. So when we devise and develop a costly HILS for DC-DC converter, it should not end up by validating a small part of this range, thus limiting the scalability for future. Also, we have to keep in mind the special features which are available in the device under test. If you take a DC-DC converter, this includes the integration of belt integrated starter generator or BIS-G in a mild hybrid vehicle on the high voltage side. Similarly, there is bidirectional energy transfer happening between high voltage and low voltage side very dynamically. And obviously, we are seeing integration of DC-DC converters with the chargers in upcoming architectures of automotive. And the sensing circuit which we have to devise for DC-DC converters should have very high accuracy and resolution. So coupling these special features with the diverse range of ratings, it becomes complex to develop a scalable HILS system for one specific ECU. It's not just DC-DC converters. We have the same problem or challenge existing for onboard charger, battery management systems, motor inverter. Each one has a very diverse operating range as well as very special and unique features which gets added more and more as the time progresses. So the question is how to design a HILS which can be used in future for other variants, types of EVs, devices with different ratings and smart features. Let us summarize the main challenges in the EV ECU validation here. As discussed, HILS scalability is a challenge. For the investment made, how to increase the return of investment. How we can ensure maximum reuse of HILS hardware, software, sensors, supplies, loads, etc. How to handle multiple variants of the same ECU, various EV categories like plug-in, series, parallel, hybrid, etc. Because each one has a different architecture and hence the validation strategies also differ. Next challenge is safety. How to ensure safety of devices used, employed engineers, what are the infrastructure requirements, approvals needed, is the earthing, isolation, grounding proper? Next challenge is how close to the real world. We are replacing real world plant with simulated plant using software and hardware. How well these simulations replicate real world behavior? Can it recreate the exact ripple dynamics, non-linearities as in real world? And the next challenge is which type of testing is required. Each type of testing has its own advantages and cost implication. Which one to choose is mainly a trade-off. Signal level versus power level, automated versus manual testing, environmental testing, gray box testing, homologation and standard testing. It is challenging to execute type approvals in lab as most of them need real vehicle testing. We will be trying to address these challenges in this webinar using eMobility HILS. This is an introduction to eMobility HILS solution. Tata Elxsi's eMobility HILS is a lab-based solution for the validation of EV systems such as battery, inverters, DC-DC converters, etc. using the concept of HILS, which can be used for validating different types of testers like drive scenarios, diagnostics testing, range verification, functional testing, drive cycles, electrical compatibility, network testers, standards verification, load testers, and performance analysis. eMobility framework, which is part of eMobility HILS, is a collection of readily available components like graphical user interface, planned models, test automation framework, and a rich test case library for EV validation. We have a full-fledged test bench with dyno load control for motor inverter validation as well as the powertrain validation. Option to add simulated environments, drive scenarios, and vehicle dynamics is also present. We have 90% automated real-time testing available. There is also an option to extend EV validation to complete interconnected vehicle level HILS, where a scalable validation test bench to support autonomous driving or AD and ADAS, infotainment, and even telematics ECU is available. Let us speak about the DC-DC converter power level validation architecture. As you can see, the DC-DC converter or the DUT is placed inside a thermal chamber for temperature derating functionality validation, and it is also connected to a chiller for proper cooling of the DUT. A programmable 2-quadrant power supply which can act as a power source or load is connected at one side, while a programmable DC electronic load is connected to the other side where energy sinking is happening. The reason being, DC electronic load supports more modes like constant current, constant voltage, custom load waveforms when compared to 2-quadrant power supplies. High resolution, high accuracy voltage sensors, current sensors are employed at both sides of the DUT in a circuit to measure exact input and output voltage and current of the DUT. Optionally, precharge circuitry will also be made part of this circuit. This photograph shows such a power sensing circuit we developed. Power supply, load, sensors, precharge circuit, chamber, chiller will be controlled and monitored by the HILS system, which houses the test automation framework, the test cases, plan models, and the GUI, which we call the eMobility framework. This is the GUI used for the validation of DC-DC, and I will use it to explain how we are performing efficiency test case validation. This represents the HV voltage and current. This represents the LV voltage and current. As you can see, when we increase the HV voltage to around 260, the device turns on and you have 12 voltage at the output. Then we use the DC electronic load to take a sinusoidal current waveform from the output of DC-DC and measure the efficiency or the output power by input power and make sure it is within the allowed range. In addition to the GUI, we have custom device drivers for the power devices, as well as plan models for ripple measurement, pre-charge, etc. And all these GUI plan models, along with the test case library, comprise the eMobility framework. Scalability levers for DC-DC HILS are selecting sensors with wide operating range, ones which can be detached from the power circuit, selecting power supplies and loads which can be stacked up in future for increasing the rating, the ones which have bidirectional capability. Individually, it should have high slew rate as well as large operating range. Similarly, the chiller and chamber selected should also be having maximum capacity. Let us take a look at the BMS signal level HILS validation architecture. Battery simulator is used for simulating the battery and real battery is not used. Battery simulator creates cell tap voltages and currents based on the information given from the HILS. HILS is capable of creating this cell tap voltage and current based on the intelligent cell model which is running inside the HILS. Cell tap lines will be coming from battery simulator and going to fault insertion unit or FIU. FIU allows you to add faults on the individual cell tap lines so that we can see how BMS responds to that. Auxiliary power supply is also given to BMS ECU. And also simulated I/O channels and vehicle network like CAN is also coming from HILS to BMS. Some examples of the simulated I/O channels are pack current, pack voltage, etc. Since we are not using the actual battery, all the battery pack related parameters will be simulated from the HILS. This is in line with the whole cell model which is running inside the HILS. Such a HILS system can be created for validating different BMS functionalities like cell balancing, normal charging, normal discharging, SOC computation, SOH computation, etc. Main scalability levers for the BMS signal level HILS are selecting the right battery simulator. There are simulators with wide voltage and current rating per cell. For example, there are cell simulators with 0.5 amps or 1 amps cell capacity, sink or source. So we have to select the right one, keeping in mind the future requirements as well. There should be an option to stack up individual battery simulators so that we can go to any number of cells as per the requirement. The cell model created should be variable enough for accommodating different chemistry, different capacity as well. Cell model is the brain of the BMS signal level validation HILS. Cell model, which is part of eMobility framework, is shown here. It's having current against time as one of its input. Other inputs are initial state of charge or SOC in percentage, battery capacity in AH, temperature against time, and the outputs of the cell model are final state of charge or current SOC in percentage, terminal voltage, and state of health or SOH all against time. The cell model is using a second order Thevenin model for the cell modeling, where state of charge is estimated using Coulomb counting technique. Extended Kalman filter or EKF based recursive predictive algorithm is used for bringing in real world nonlinearities and dynamics. We impart the impact of temperature on the internal resistance of the cell. And finally, the state of health is computed from capacity depletion technique. Here we have shown some graphs which we got from the real-time cell model. The first two graphs corresponds to the state of charge in percentage and the terminal voltage of one cell plotted for a constant or a same value of current waveform as it is shown here. It is evident that a negative value of current which corresponds to charging is increasing the state of charge, which is getting capped at 100%. Similarly, a positive value of current or the process of discharge is reducing the state of charge of the battery. Similarly, same impact on the terminal voltage can also be seen, where charging corresponds to increasing of the cell terminal voltage and discharging corresponds to reduction of terminal voltage. And finally, we also have the impact of temperature on the internal resistance of the cell. This cell model can be used to create a battery model by connecting individual cells in series and parallel based on the configuration we have, which can be used for validation of any BMS. Let us take a look at the BMS signal level validation GUI part of the eMobility framework. What you are seeing currently is a test case which is being executed for cell balancing. As you can see, individual cell voltage can be shown in this GUI, where we have purposefully created a single cell to be an over voltage as compared to the nominal voltage in the other cells. This specific device under test, the battery management system ECU, is having passive balancing feature, which means it will use an internal shunt resistor circuit to dissipate over voltage cells current as compared to normal voltage cells. And you can see we have shown the current which is flowing in that shunt resistor or in the individual cells near each cell. And you can see the shunt current is high for the over voltage cell as compared to other normal voltage cells. And you can also visualize the fault status here, where this line will be broken or open or short to other line, etc. The same GUI can be used for visualizing the pack voltage parameters like state of charge, state of health, average cell voltage, pack current, etc. The floating graph gives you an overview of individual cell voltage as well as the pack voltage. The GUI also gives an overview about the diagnostic trouble codes as well as the health status of the ECU. This is the BMS power level HILS architecture, where the fundamental difference of this from the BMS signal level architecture is the usage of real battery pack. Battery is connected to BMS as in real vehicle, and it is enclosed inside a thermal chamber, and the battery pack is also connected to proper chiller mechanism for cooling. This allows us to validate the temperature dependent test cases. There must be a mechanism to charge and discharge the battery pack as in real vehicle. So what we use for that is the battery cycler, which is again a programmable device which will be connected to the battery terminals. Battery cycler allows the battery pack to be charged, discharged based on specific drive cycle patterns, which will be controlled by using a plan model running inside the HILS. BMS signals will be monitored and the IOs will be analyzed using simulated IO channels of the HILS simulator. Scalability levers for BMS power level HILS are choosing the right battery cycler, being a costly device. Next one is the battery. If you are choosing the battery for BMS power level HILS, we have to keep in mind the scalability and modularity of the battery pack, meaning you should be able to add or remove modules for increasing or decreasing the capacity. This is the motor control unit signal level validation architecture. Motor control unit is the only real entity used here, where inverter and motor are simulated using software models which are part of the eMobility framework. Inverter and motor model will be running inside real-time high-frequency hardware like FPGA, which is part of the HILS hardware. Motor control unit will be generating the gate drive signals or the PWM signals, which will be captured through the IO channels of the HILS and given to the inverter model. Inverter model uses this to generate the phase voltage values, which is given as the input to the motor model. Motor model will be generating the phase currents as well as the sensor position feedback and giving it through proper IO channels of the HILS to the MCU. And over CAN, MCU will be connected to the HILS, which allows the HILS system to give the required control values to the MCU. And you can see that MCU is in a closed loop, which allows us to validate different control algorithm functionalities of MCU like DTC, FOC, etc. The main scalability levers for motor control unit signal level are selecting or developing the proper motor model which can cater to different types of motors and configurations. Similarly, different types of inverter should also be considered by the inverter model. And when you choose the FPGA hardware, you have to keep in mind the latest motor simulation toolkits which are available in market as well. This is the motor control unit plus inverter power level HILS architecture. As you can see, real battery pack is used as the energy source, where MCU plus inverter will convert this DC battery voltage to AC voltage based on the requests coming from the HILS. Motor whose shaft is extended through a torque sensor is connected to a dynamometer or dyno. Dyno is controlled by an AFE VFD panel, where AFE stands for active front end and VFD stands for variable frequency drive. This panel is connected to the power grid. VFD is a device which converts input power of constant voltage, constant frequency to output power with variable voltage and variable frequency so as to control dyno based on the requests coming from the HILS. AFE is a device which helps us to convert the energy generated from dyno to a proper format which allows us to push it back to the grid. Let us explain with an example how this system can be used for creating a loading effect on the motor. HILS will give a required loading torque over communication line to VFD. VFD converts this loading torque to a specific current value, and it tries to generate that current value from dyno when it is made to act as a generator. Generation of energy from dyno will create a mechanical loading effect on motor because both are coupled through a common shaft. The mechanical loading effect which this motor now experiences is equal to the initial loading torque which we gave as input to VFD. Since dyno is generating energy, the generated energy will be converted to a proper format by AFE and pushed back to the grid. Now, using this setup, we can expose the motor to different drive cycle patterns like going uphill, downhill, and even regenerative braking. Main scalability levers for this setup is choosing the right dyno, because the existing motors have a wide range of torque, speed, and power. Sometimes the torque and speed values are very high that we might need a gear mechanism connected to the dyno. Infrastructure requirements are huge, especially when we need to go beyond a power level. We have to get special approvals. Of course, we can use a thermal chamber and chiller for validating temperature related functionalities of MCU plus inverter as well as motor. So we have to keep in mind the capacity and ratings of chiller and the thermal chamber as well. This slide speaks about the vehicle drive cycle data available for the validation of motor control unit plus inverter at power level. As you can see, we have graphs of vehicle speed against time as well as dynamometer torque against time for different real world patterns which can be used to excite the HILS setup. Tata Elxsi also has strong experience in building custom 3D scenario creation tool with 3D visualization and vehicle dynamics. What you're seeing are the actual photographs taken from such simulators built and integrated to eMobility HILS. The latest concepts of game engine technology is used to generate photorealistic 3D animation and to link it with real-time models running inside the HILS, especially the dynamometer control as well as the motor control for the ego vehicle motion. This is the onboard charger power level HILS architecture, where onboard charger is connected to charging station emulator, which is a programmable device which can be used to simulate different charging standards like CHAdeMO, CCS, etc. EVSE simulation can be implemented using charging station emulator based on the drive cycle data inside the HILS. At the output side, OBCM will be connected to either a battery pack or a programmable DC electronic load based on the requirement. OBCM will be kept inside a thermal chamber and connected to a chiller for implementing temperature-dependent test cases. A power analyzer will be used for measuring the voltage, current, and other power parameters at both the input AC as well as the output DC. All the programmable devices will be connected to HILS, and this setup can be used for validating different charging standards as well as bidirectional energy transfer. Main scalability levers are selecting the proper battery cycler, power analyzer, and the stack of options for increasing the capacity of power analyzer, battery pack, load, or even emulator. Then the charger models that we have to develop should be scalable enough for different geography standards. Let us take a look at the standards that can be validated using eMobility HILS. IS 17017 for charging systems, AIS 041 for motors, IEC 61010 for sensing circuits, AIS 040 for battery, CHAdeMO for charger, homologation, vehicle type approval, etc. The main challenge of homologation or vehicle type approval is most of the subjects and the regulations are speaking about using real vehicle. But we can bring a part of this into lab-based testing by following the approach shown here. Through detailed analysis of standards, we were able to devise solutions where real plant is simulated with simulation. A subset of standard requirements is thus taken from vehicle testing into a lab-based environment, where the rest can be tested in track or real world. We also have process compliant validation, like for example ASPICE, and also ISO 26262 or functional safety compliant validation. Let us take a look at how eMobility HILS is used for ASPICE compliant validation. ASPICE is for SysFi or System Integration Test SIT, and System Qualification Test SQT is performed as shown here. For performing SIT, the inputs which we need are System Architectural Design or SYAD, Hardware Software Interface Specification or HSIS, which we will be using to create proper bidirectional tracing between the pins and the interfaces. System level FMEA document is also referred for creating the SIT test plan sequentially after creating the interface mapping and getting approval. Then we will focus on creating test cases once we have the approved test plan in place. Test cases will be executed based on the strategy which was commonly agreed, which will be finally used to generate test reports, log files, bugs, etc. Bidirectional traceability will be maintained when and wherever possible. Stringent review process is happening for each artifacts. When you take a look at system qualification test or SQT process flow, it starts with the technical specification document and the system requirement specifications as the input, from which we will create the high-level design or the HLD, which we will convert it into SQT test plan. Test cases will be derived once the test plan is approved. Test execution will happen, and finally test reports will be generated. SQT artifacts are also exposed to stringent review process, and at each stage relevant and required approvals are taken. This is followed in multiple projects in Tata Elxsi to make ASPICE compliance. Let us take a look at the advantages of eMobility HILS. Close to real world. Real world replication in lab due to the accurate plan models helps us to recreate dynamics, real world ripples, etc. Another advantage is the high scalability. As we have been discussing through the previous slides, since we are having reusable hardware and software modules, high scalability is assured in eMobility HILS. Cost efficient. Due to the flexible business models that we are going to discuss in next slide, we are having a cost efficient solution. Faster time to market. There is practically zero lead time because we have costly and complex power electronic devices readily available for starting the test execution from day one. eMobility framework, which comprises of test cases, software modules like plan models, test automation suite, GUI, drive cycle data, all can be reused fully or partially or even after customization based on the requirement at hand. This actually saves a lot of effort. We also have a rich library of EV test scenarios, which can be used for EV ECU validation. All this helps us in reducing the time to market when coupled with the typical advantages of HILS as a strategy has. Let us take a look at the business models for eMobility HILS. The first business model is validation as a service, where you need to pay only for the usage charge for the components that you are using for a predefined amount of time. Tata Elxsi takes the complete validation ownership, where you have to provide us only with the device under test and the supporting documents. Another business model is platform licensing, where we develop new HILS at your facility for you. Still, we can reuse most of the already available eMobility framework components like test cases, plan models, test automation suite, etc. While we also need to develop new test cases and updations in the plan models based on new requirements. Let us take a look at the validation as a service case study. The case study involves a 48 volt to 12 volt bidirectional DC-DC converter ECU validation for an OEM. The inputs which we got from the customer are the requirement specifications, the communication files, the device transmittal and IO CARA, flashing procedure, safety requirements, and the device under test, the physical unit. The HILS reusable items were the test automation framework, the generic test cases which were created for DC-DC, HILS hardware, HILS software, sensing circuits, etc. HILS modification was performed on the communication or the RSBus simulation, the HIL harness and the IO model, and also to create OEM specific test cases. And finally, we got the updated eMobility HILS based on the new requirements and the ECU specification from the customer. Final deliverables to the customer were the final test cases, test reports, bugs, updated plan models, and log files. Finally, let us summarize the savings achieved for the specific validation as a service case study discussed in the previous slide. When we used eMobility framework for HILS setup and validation time for one software drop, around 50% savings was achieved due to the reusable modules. And when you take a look at the percentage of reuses, there was a 40% reuse of test cases, 50% reuse of plan models, and 90% reuse of test automation framework. And the savings achieved due to the usage of eMobility HILS, especially from a hardware point of view. We have achieved around 74% cost savings to our customer when we compare it against setting up a new HILS at customer site. I would like to thank all the attendees of the webinar, and I would like to also thank Automotive World for organizing such a platform for me to present our solutions on eMobility HILS. If any of the attendees need to have any more information on the solutions which were proposed as well as to know more about the offerings, please feel free to contact in this information.